So if we look at an example, there's a lot of really good stuff right here. Let me start a new page. Suppose I have the series, if k starts at 1 and goes to infinity, of 1 over k to the 8th power. So we're thinking about the function f of x equals 1 over x to the 8th, which is on the interval from 1 to infinity, decreasing, continuous, and positive. The upper bound for the remainder is going to be the value of the integral from 1 to infinity of 1 over x to the 8th. So I'm going to write that as x to the minus 8th power. So we work this integral. Nope. 1 over 7x to the 7th evaluated from 1 to b. Okay, I did a couple of things together. So we're looking at negative 1 over 7b to the 7th minus negative 1 I'm sorry, I set that up wrong. It should be an integral from n to infinity. There, that looks like what I expected to see. Then taking that limit, we see that the upper bound for the remainder is 1 over 7n to the 7th power. Now the kind of thing that you're going to see that you need to do with that is to figure out how many terms do you have to have in your partial sum to have the amount of error, to have the remainder be less than or equal to a certain value. So in this example, we want our remainder to be less than or equal to 10 to the minus 3rd power. And the question is, how many terms, what's the value of n to make this true? Well, if our remainder is less than or equal to 1 over 7n to the 7th, we'll put that less than or equal to 10 to the minus 3rd power. So cross multiplying, since we're talking about a positive value of n, multiplying both sides by 7n to the 7th, it's not going to reverse the inequality sign. We'll look at 1000 less than or equal to 7n to the 7th. Solving this for n then. Divide by 7 and take the 7th root. So if you grab your calculator and plug in that number, you're going to find that this is 2.0316 or so. That's less than or equal to n. So n is a counter. It's got to be 1, 2, 3, 4, and so on. So we want the smallest value of n that satisfies that statement. So we're going to need 3 terms. So n equal 3. So what are we saying here? We need to add 3 terms to approximate the series and keep the error less than or equal to 1,000th. Alright, now let's find an upper bound and a lower bound for the sum, the actual sum S for this series. The lower bound is the nth partial sum plus the integral from n plus 1 to infinity of our function f of x. Okay, now we've already done some of the work for that definite integral. The difference is we just have a different lower limit. This is going to end up being, and I'll leave it to you to work out, 1 over 7 times n plus 1 to the 7th power. The upper bound for the sum of the series would be s sub n plus the integral from n to infinity of x to the minus 8th power. Which ends up being 1 over 7 n to the 7th. Again, we've already done that work. So if we look at the sum of the first 10 terms, so if we consider n equal to 10, the value of the 10th partial sum we can get using our calculator. And I'll show you how to do that. Okay, using your calculator, if you press alpha table set, alpha window, the second option in that menu you see is a sum. It's going to pop the sum notation in your screen exactly the way you would write it. You can use whatever index you want to. This is set up with K, so we'll go alpha, if I can find K on my calculator, there it is. Alpha K is going to start at 1, and we're going to 10 because we want the 10th partial sum. And then our expression is 1 over K. You got to use the same index here, raised to the 8th power. Okay, now you're going to get a pretty small, in this case, decimal number. You don't want to round that number off. So here's what I would recommend doing. Store that as variable A. Okay, so what we've done in our calculator is we've stored this as A, and it is approximately 1.004077346, etc. Okay, so that's stored as A. So if we're wanting to evaluate the lower limit, we've got our number for s of 10 plus 1 over 7 times 10 plus 1 is 11 to the 7th power, and I'm going to evaluate that. I'm going to get a decimal number again, and I'm going to store that maybe as B. So grabbing my calculator, I have A plus the fraction 1 over 7 times 11 raised to the 7th power. Oops, I left out a parenthesis. There we go. Okay, evaluate that. And let's store that as B. So store alpha B. The number we've got is 1.004077354, and we've stored that as B in case we need that for something later. Then the upper limit, and we're doing this at n equal 10, so this ought to be L of 10 and U of 10. That's going to be S of 10 plus 1 over 7 times 10 to the 7th power. So U of 10, I might store that as C when I get a value. Grabbing Mr. Calculator, I have alpha A, so that's the value of S of 10, plus the fraction 1 over 7 times 10 raised to the 7th power. Okay, so that is approximately 1.004077361. Now you can see how close these two numbers are. That's a decimal point right there. So this is actually, if we use n equal 10, we're able to narrow down pretty closely to get a pretty good estimate of what the actual value of the sum of the series is. It's going to be about 1.00408 if you round it off to, what would that be, 5 or 6 decimal places, which is pretty accurate.